We'll complete Module 4 by talking about the incidence of molecular dipole moments as one of the consequences of different molecular shapes and the polarity of their bonds. Our learning goals will include the origin and nature of molecular dipole moments and their relation to bond dipoles, which is a more localized measure. Bond dipoles are basically what happens when we take the shared electrons between atoms that shift because of the different electronegativities and form a polar covalent bond. So that shift of electrons is going to create a charge separation, as we noted in hydrogen chloride, where you'll have a positive end and a negative end to the bond. That charge separation basically defines what we know of as a bond dipole. All right, so once again, looking at hydrogen chloride, we have a positive end at the hydrogen end and a negative at the chlorine end. The bond dipole basically is a vector that points from the positive end to the negative end, and the length of that bond dipole tells us something about the degree of charge separation that occurs there. All right, so it is a vector quantity that describes something about charge separation. We can also represent a dipole more abstractly using a diagram like this, where we have a positive end and a negative end, and there is a separation between those charges. So anything that has this sort of charge separation behaves physically like a dipole. The bond dipole is a vector that is along the bond, so it's parallel to the direction of the bond, and it points toward the more negative end. The magnitude of that bond dipole is basically equivalent to the partial charge times the bond length. So this gives us another way of quantifying, if you will, the positive charge that is occurring in a polar covalent bond. Now when we talk about these bond dipoles, they have a bond dipole moment, which is the strength of that bond dipole. While the bond dipole itself is a vector, the dipole moment basically tells us the length of that dipole vector. So it is the charge, which we might represent by delta, times the length, which is just the length of the bond. Now dipole moment units are given in a unit called debye. And to give you an idea of how big a debye might be, if I had a proton and electron that were separated by 100 picometers, which is about the length of a bond, this would have a dipole strength of 4.8 debye. All right, so that gives you a measuring stick for understanding this. So if we have several bond dipoles, and we'll take a look at a few representative ones, that carbon-oxygen double bond has a very strong bond dipole. It's 2.33 debye. Whereas OH, which is also a very strong bond dipole, is 1.55. Carbon-hydrogen is not a strong bond dipole, so its dipole moment would be 0.35 debye. So this allows us to look at something like acetic acid, which is shown over here, and quantify the length of the bond dipoles in each of these different atoms. So, in each of these different bonds. So the carbon-hydrogen has a length of 0.35 debye. The carbon-oxygen double bond has a length of 2.33 debye, and the bond dipole for the oxygen-hydrogen bond is 1.55 debye. So you might ask, well, okay, I want the total molecular dipole moment of this molecule, acetic acid. Can I just add these numbers together? Well, that would be great if we could, but the answer is no, we cannot. We need to consider the fact that these bond dipoles are actually vectors, and they point in different directions. So now I want you to imagine, like the one we just saw, a molecule with multiple polar bonds. The way we would describe the net effect of the bond dipoles is to consider the directions of those bond dipoles, some of which are drawn here, and what would happen if we added up all these vectors together. The total dipole for the molecule is going to be the sum of the bond dipole vectors. All right, well, this means we need to know a little bit about vector addition. So how can we do vector addition? Okay, these represent the net properties of a series of vector movements. We can think of vectors as instructions that tell us how to move from one point to a new point by going a certain distance in a given direction. So two successive instructions might be drawn as follows. I'm starting with a first instruction where it tells me to go sort of toward the northeast direction by a certain length here. And then I'm given a second direction which says move sort of west northwest in another distance to go there. So at the end of those two instructions, I will have moved from the bottom point all the way up to where the second arrow ends. So in other words, this would be my net movement. That's the net instruction. That net instruction is, in a sense, the sum of those two vectors. Now, if I had decided to follow the second instruction first and then follow the first instruction, notice that I end up at the same point. So the order in which I add vectors together doesn't matter. They always end up with the same sum. We can think of the vector sum as being like a shortcut. If I had started at my initial point and just gone directly along the sum vector, that would have been the shortest way to go to the end point of that two instruction set. So this is another way we can think of these vector sums, as they provide us the shortcut between the beginning and the end of our various movements. So let's apply this now to understand something about the water. Water has two polar bonds and a bent geometry. Okay, it looks something like this. The angle between those bonds is 104.5 degrees. You'll notice that this is less than the tetrahedral angle because the lone pairs, the non-bonding pairs on the oxygen, tend to push those two bonds closer to one another. So we have two bond dipole vectors that look like this. They point from hydrogen to oxygen. They have a length of 1.55 dpi. And what we want to do is figure out what is the net dipole when I add these two bond dipoles together for water. So the total sum is going to be the sum of those dipoles. So I start with one. It gives me an instruction to move up and to the right. The second one gives me an instruction to move up and to the left. And when I add them together, I will end up with a net instruction that says move straight up a distance of 1.88 dpi. Now, I want to be very clear that the lengths of these vectors is the dipole moments. The length plus the direction of the vectors is the dipole vectors. You should note, especially in this case, that we couldn't just add 1.55 with 1.55. These are the lengths of the two bond dipoles in water. That does not give the dipole moment for the water molecule. So the vector sum is not the same as the arithmetic sum. So here is our water molecule. Here is its net dipole, and you can see that it goes right up through the middle of the molecule, oriented in a very symmetric way with respect to the two OH bonds.